All right, the last video we were interested in the monotonicity, or where a function was increasing or decreasing or constant, and we used the first derivative to determine that information. But when you're increasing, you can be increasing at a constant rate, or increasing at an increasing rate, or increasing at a decreasing rate. And the same thing for when you're decreasing. And those means of, or the way we describe those sort of behaviors is where we get into the shape of the graph, or what we call the concavity. So let's talk about the concavity. Let's look at a function f that's differentiable on an open interval. Then the function f is said to be concave upward, or concave up, on the interval from a to b if f prime is increasing on that interval. So notice this, that we're concave up if f prime is increasing. Real important to realize that f prime increasing is not the same thing as f prime being positive. So increasing does not mean positive. A function could be increasing below the x-axis, where the values of the function are negative. It could be increasing above the x-axis. And so be careful of that. We, of course, used in the previous lecture about monotonicity, we used the fact that f prime, if it was positive, the function was increasing. But if f prime itself is increasing, then the function f is concave upward. Let's take a look at the shape over here, concave upward, see if that makes sense. If I look at the tangent line at some point, let's pick, this point right here. What's the tangent line look like at the top of my ruler, right? And and think about the slope of this tangent line. It's going to be negative, right? Going down as we run over there, so the slope is negative. But as I move from left to right, now here's my tangent line, still negative, but a little less negative, right? It's actually, going from, like, I don't know, for instance, this slope here might be negative 5, right? Go down 5 units and over 1, for instance, I don't know. And then here would be what? More like something like negative 3 or something. Go down 3 units and over 1. So it actually is increasing, right? Negative 5 to negative 3 is an increase. As I continue to move around this curve, right, eventually what happens, I got negative slope, negative derivative, right? Until right there at the bottom, right, we know we have a horizontal tangent line, the derivative is 0 right there, where we have that minimum right there. And then what happens is we continue to move, well, towards the right. Then we turn from to a derivative that's now positive. So as I'm moving from left to right, the derivative is increasing. Do you see that? The slope is increasing, right? And this shape that we get is what we call concave upward. It's an easy shape to remember. If you think of concave upward, when you're up, you're happy. You've got a big smile, right? So there it is, a big smile. And it's real important to see this part of the graph, we're decreasing, but we're concave up. Here we're increasing, but we're concave up. Over this entire interval, what must be true? F prime is increasing. Notice for this portion of the graph, F prime is increasing, but F prime at any instant in there is negative, right? The slope is negative, but increasing, right? And then on this branch, if you will, as we move from left to right, the derivative F prime is still increasing, but at any point F prime is positive. So if F prime is negative, we're decreasing concave up. F prime positive, increasing concave up. Over the whole interval, F prime is increasing. Similarly, we say that F is concave downward or concave down on an interval if F prime is decreasing on that interval. So here's the concave down situation, right? And look at my slope at a point here. Slope, the derivative is positive, and as I move from left to right, that slope is still positive but getting smaller, right? It's decreasing down all the way till we get to the top there at 0, and then what? On this side we become negative. So as we move from left to right, the derivative is decreasing. But notice the derivative is positive on this branch, so that we're increasing concave down. Derivative on this side is negative at any point, but still decreasing. So the function is decreasing, and we are concave down. So be careful. You've got to differentiate between, as I said, the function is decreasing here, and the derivative is decreasing. Here the function is increasing, and the derivative is decreasing. So it's real important to understand what's increasing, what's decreasing, what's positive, what's negative. But this is concave down. Again, it's easy shape to remember. When you're down, you're sad, you frown. Here's your frown, okay? So concave upward, concave downward. All right, so that's how we can describe concavity. Now, when we're actually going to test for concavity, it's not always easy to look at the graph and see if you see this shape. Way over here, if I look over here, this is concave up, right? But it looks almost linear, right? If a function's linear, there's no concavity, because for linear functions, f prime is constant. For linear functions, f prime is not increasing, nor is f prime decreasing, right? For lines, f prime is constant. So it looks almost linear here. So it's a lot of times portions of the graph that are concave up or concave down, it's hard to tell just by looking at it. So we need an algebraic method for doing that. And here's what we do. Notice if f prime is increasing, what do we know about the derivative of f prime? What is the derivative of f prime? That's the second derivative, right? So if f prime is increasing, what do we know about the second derivative, f double prime? Well, if f prime, the function, is increasing, f double prime must be positive. And what happens when f prime is decreasing? Its derivative, f double prime, must be negative. And that's the way we're going to test for concavity. So assuming that the second derivative exists for all x in an open interval from a to b, if the second derivative is positive, right, on that interval, then f is concave upward. If the second derivative is negative, then f is concave downward. This is the way we usually test it algebraically. So again, important to understand the relationship here. Second derivative is positive, means that f prime is increasing, which means f is concave upward. F double prime being negative means f prime is decreasing, and f is concave downward. So it's real important to understand those relationships. We'll look at a quick example here of that. And now, one thing that can happen is you can have a graph that, for instance, is this portion. What do you think? Concave up or concave down? What's this going to be? Looks like it's part of a frown, right? It's this part, right, like here. So it looks like we're concave down. But then, all of a sudden, there's a change, and all of a sudden it's now what? Concave up, right? Concave up. So this point is an important point. I can also be changing from concave up, right, to concave down, right? So something like that. So these points right here that we have here are points of inflection, where we have a change in concavity, and either changing from concave up to concave down or vice versa. So points of inflection or inflection points. Now, how do we test for inflection points? Well, we're going to piggyback on what we did up here. If there's going to be a change in concavity, a change from upward to downward or from downward to upward, there must be what? A change in the sign of the second derivative. Very important there. So if f double prime exists on the open interval about x equals c, except possibly at c, so we could have that the second derivative doesn't exist at c, but if that second derivative is 0 or undefined, and, right, real important here, right, f double prime rather changes sign at x equals c. So it must change sign then f of x has an inflection point at x equals c. Okay. All right. Let's see if we can first think of this just from a graphical example, and then we'll look at some algebraic ones. So I want to take a look at this function, which is similar to the way we started when we talked about monotonicity. Again, these values of a all the way through j are input values. So here's the x-intercept for the function. B here, this looks about location where we have a local max right there, right? C right here. Now I wonder what's going on right there. Think about that. D, intercept there. E, that point there. What's going on there? F, that looks like a local max. G, intercept H. Right there. I, local min again maybe. J, x-intercept. So those are the important points of this graph. Now, if the above is the graph of the function f, let's give the following. Where is the function concave upward? So where's the graph smiling at you? Right? Where's it smiling at you? Well, here's a portion where it's smiling right here. Okay. Looks like this portion to me, you know, again, it's hard to tell exactly. It looks almost linear right here. But this portion here looks like it's part of a frown. Here's the down part, right? But right about C, there's a change, right? It looks like right about C, there's a change. And all the way to E, notice after E again, you know, it looks like we're part of a frown. So here's the smile part. The derivative is increasing over this interval. If I draw the tangent line, right, the tangent line's negative here, going to 0, and then it's positive. So I would say from C to E. Where else? There's another location, right? Again, from E all the way, looks like to me to H. So this part still looks like it's a frown all the way down here, and then what? Here, though, we have a smile, so to speak, right? And again, it looks like it's almost linear as we get up here, but we're going to go ahead and say from H to infinity. Okay. Now, where is the function concave down? Where it's frowning, right? So everything less than what? C, all the way up to C. And then we have a frown again, right, from E to H. Okay. Now, somebody might say, it looks to me like, you know, I don't know, maybe they think it's linear here, like it's like a line. And you could have a portion of the graph where there's no concavity, which would not be included in either of these intervals. Like you could have gone from E to G instead of E to H. But that will affect there. Inflection points are points where it changes concavity. And so that should be consistent with what you have here, right? Where do we have a change in concavity? We say it's concave down until C, and then after C it's concave up. So at C we have a point of inflection, right? Notice it's concave down all the way up to C, and then from C to E it's concave up. So at C there's a change in concavity. So I'm going to include C. Where else? Also at E, right? From concave up to concave down. And then lastly at H, right? Concave down to concave up. And these are consistent with what I have up here. Real important. A lot of students mess these things up in these. You want to check and make sure they're consistent. Right. So from concave down up to C, after C concave up, C must be a point of inflection. Right. Up C to E it's concave up, and then from after E to H, right, concave down, right at E, change of concavity. Okay. Now, let's mix it up a little bit. We're going to do two more iterations of this problem. First here we said this is the graph of the function f. Now I want you to use the graph above for the f prime, the derivative of f. So this now is no longer f. This is f prime. This is the derivative of our function. This is the derivative of our function, right? Okay, and what I want to know again is where is f in this case, concave upward. I don't have the graph of f anymore. I have f prime. So what did we say? What do we know? F is concave upward. What's happening to the derivative when f is concave upward? What was the definition? F is concave upward when F prime is increasing. Right, F prime is increasing. So when I look at the graph, what am I going to be looking for? Since it's the graph of F prime, I want to look where it's increasing. Where is it increasing? That will be where the graph of the function f, which I don't have a graph of, not asking you to graph it. That's going to be where the graph of f is concave upward. Okay, so where is f increasing? It's going up, 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 for all values less than b, right? All values less than b. Then where? Sliding down. At d, it does what again? Starts going up all the way to f, starts going down, and then from I on to infinity, right? So everything less than b, everything between d and f, and then everything greater than I. That's where f prime is increasing, hence that's where f is concave upward. Or is f going to be concave downward? F prime is what? Decreasing. So where's f prime decreasing? From b to d, and from f to I. B to d and f to I. Where does the function f have inflection points, or points of inflection? Right? Well, we can do it really from here. We could do it from here, right? We're saying we're concave upward up to b, and then from b to d, we're concave down. So b has to be an inflection point. From b to d, we're concave down. D to f, we're concave up. So d. From d to f, we're concave up. F to I, concave down. So f has to be. And finally, from f to I, we're concave down, and then from values greater than I, we're concave up. So I, right? I can do that just based on this, assuming this is correct. But notice we can do that. And what do we note about B, D, F, and I on the graph of f prime? What are those? What's happening to the graph of f prime at those locations? What's happening to the graph of f prime at B, D, F, and I? I hope you're saying there are local extrema, local max, local mins. And you'd be correct, right? Because we're changing from increasing to decreasing at B. B has a local max for f prime. But notice that gives rise to points of inflection for the graph of f. Okay. D is a local minimum for f prime, right? But we're changing what? From f prime decreasing, which means f is concave down, to f prime increasing, which means f is concave up. So D would be a point of inflection for the graph of f. Okay, so again, make sure your answers are consistent here. Last iteration then, so we've looked at this functions here being the graph of f, and then f prime. Now I'm going to say this. This is now the graph of f double prime, the second derivative of the function f. If this is f double prime, answer the same questions. Where is the function f concave upward? Now again, I don't have the graph of f. I'm not asking you to construct the graph of f. What I am giving you is the graph of f double prime, the second derivative of f. So what do we know? F is concave upward on an interval if what? What is true of f double prime on that interval? F double prime is what? Greater than 0. It's positive, which does not mean increasing. It's positive. F double prime being positive means f prime is increasing, means f is concave upward. Those are all equivalent statements. All right, so what am I going to do? I'm going to look where f double prime is greater than 0. This is now f double prime. Where is the graph greater than 0? When it is above the x-axis. So where is it above the x-axis? Well, at A, it crosses through, so it's now above from A, what? To D. Now D, it just touches right there. It's just 0 right at D, and then it continues to be what? Above and to G. So you could do A to D, and then D to G. I'm just going to go from A to g, because there's just one point, right, where it's just 0. Okay, so I'm going to go from a to g. If you want to go from a to d and d to g, that's fine. Where else are we above the x-axis then? We're below from g to j, and then j on to infinity, so everything greater than j. So I'm just going to go from a to g, and then from j to infinity. Where is f concave downward? Where the second derivative is what? Less than 0. Second derivative less than 0 means f prime is decreasing, means f is concave downward. So where is f double prime less than 0? Where it's below the x-axis. That occurs for values less than a and between g and j. Less than a and between g and j. And then, inflection points. Again, you can get it right from here. What are we saying? We're concave down for values less than a, and then after a, from a to g, we're concave up. So a has to be a point of inflection. Concave up until g, and then we change from g to j, we're concave down. So g. And last but not least, then, from g to j, we're concave down. J to infinity, we're concave up. J is as well. Okay. Now, go back to the graph. What's happening to the graph of the second derivative at a, g, and j? Where our function f has points of inflection. What's happening at a, g, and j? The second derivative is 0. But not just that. Because if you'll note, a, g, and j, right, the second derivative is 0. It's also 0 at d. Why is d not a point of inflection? Well, remember, for us to have a point of inflection, we must change concavity, which means the second derivative has to change sign, which essentially means the graph has to cross the x-axis, right? Notice at a, we're negative below, and then above a, we're positive. We change sign at a. We change sign at g from positive to negative. We change sign at j from negative to positive. So we're changing from concave down to concave up at j. Point of inflection for the graph of f. D, do we change sign there? No. Positive on one side, positive on the other. So we're concave up, right, when the second derivative is positive, less than d, and then we're still concave up. So d is not a point of inflection. That's real important because a lot of students will just say, oh, inflection points are just where the second derivative is 0. And that's not true. It has to have a change in sign of the second derivative. Okay, so that's our introduction to the idea of concavity and using, second derivative, first derivative to give the definition, but then the second derivative is a good way to test for concavity. That's the way we're going to proceed. So in the examples in the next video, we will look at some algebraic examples.